Okay, let's get started. Welcome everyone. This is our 35th online Spintronics seminar. The speaker today is Dr. Dongwook Go, and his talk will be about orbital transport and spintronics. Dr. Go received his bachelor's degree in 2013 and PhD in 2019, both at Postech in South Korea. After that, he stayed for another year there as a postdoc, continuing his work on orbital dynamics and transport in the group of Professor Hyun-Woo Lee. And in the course of his both graduate and postdoctoral studies, he collaborated with researchers at Forschungszentrum Jülich. And in April of this year, 2020, he started a postdoctoral appointment at Jülich in a group of Professor Yuri Makrousov. So with this, I'm handing it over to Dongwook, and I look forward to your talk. Please go ahead.
Yeah, thank you very much, Kirill. Also, thank you, Sin, for organizing this very nice online conference. So, so today I'm going to talk about spintronics. In spintronics, people mostly discuss spin, but in my opinion, in spintronics, what is also important is how the spin interacts with other part of the solid, like how the spin interacts with solid or thermal gradients or with light and so on and so on. So in this talk, I'm going to focus on how the orbital degree of freedom in solid will interact with spin and how we can manipulate orbital to for spintronic application and for deeper understanding of spin-orbitronic phenomena in general. So, so before going on more seriously, let's review some of the basic concepts for people who are not familiar with these concepts. The first one is spin transfer torque. The idea is that here you inject a spin polarized electron and inject into the ferromagnet. So after all this spin precession and dephasing, after all, the outgoing electron spin will be parallel to the spin of the ferromagnet. So the outgoing electron spin will be rotated. But we know that the total angular momentum of the system should be conserved. Therefore, there must be a back action on the ferromagnet as well. And this back action torque is called a spin transfer torque. So typical setup for a spin transfer torque device is like a ferromagnet and spacer layer and ferromagnet like this. And the bottom layer, called fixed layer, is used to polarize the spin. And then spin current can be injected to the upper layer, called free layer. And then magnetic configuration can be switched from down to up or up to down. It depends on the direction of the current. So this spin transfer torque requires additional ferromagnetic layer to polarize the spin. But in the last decade, people have realized that we don't actually need a ferromagnetic layer to polarize the spin. What we need is just a spin-orbit interaction. In one mechanism, spin-orbit interaction in the bulk of the material can induce the transverse spin current by a mechanism called spin Hall effect, and we can utilize this spin current to manipulate magnetic configuration. And meanwhile, there was another mechanism proposed, which is based on the interfacial state between the ferromagnetic layer and the magnetic layer. And here there exists so-called Rashba states. The essential feature of the Rashba state is the locking between the electron's velocity and spin. And therefore, by utilizing this spin velocity locking, we can also generate this non-equilibrium spin density at the interface. And in turn, we can manipulate magnetic configuration. So for all these mechanisms, it relies on spin-orbit coupling of the non-magnetic layer here in the bottom. So for example, platinum, tantalum, tungsten, and topological insulator and other strong spin-orbit materials are used. So spin-orbit torque turned out to be very useful to even very strong to switch the magnetization in experiments. Can be potentially used for magnetic MRAM. Okay, but as a physicist, I'm interested in understanding what is going on from fundamental perspective. In my opinion, spin-orbit torque can be understood as one of the more larger class of phenomena called Magneto-Electric Coupling. It means simply the coupling between electricity and magnetism in solid. Here in this simple diagram, I show you how the force, electric field and magnetic field are coupled with a coordinate. P is electric dipole moment, and M is magnetization, or magnetic dipole moments. And in between here, I schematically placed how orbital angular momentum and spin orbital angular momentum are related to force and coordinates. So one thing you notice is that for spin, we notice that unless there is a spin-orbital coupling, it couples the only magnetic part of the force and coordinates. So if we don't have any orbital, and if there is no spin-orbital coupling, it is obvious that it is impossible to manipulate the magnetic configuration by electric field. On the other hand, if you look at the orbital here, it couples to both electric part and magnetic part of the force and coordinates. And the reason is that for orbital, it's basically a charge distribution in real space by just orbital wave function. Therefore, it couples to electric part as well as the magnetic part. So in this situation, we can even imagine a kind of case where there is no spin-orbital coupling at all, but we apply electric field. And then there is going to be dynamics of the orbital that will mediate the coupling between electricity and magnetism. But once we include the spin-orbital interaction, then the spin dynamics will be entangled with the orbital dynamics. Therefore, so spin and orbital, they are entangled together, will mediate Magneto-Electric Coupling. So let's have a look at this more closely. So here, I'm going to look at what carries angular momentum in solids and how do they interact. So in solid, first of all, we are dealing with magnetism. So there is a local magnetic moment in localized D states, and also there's angular momentum in the lattice by mechanical motion of the lattice, or there is phonon angular momentum. And importantly, in spintronics, we have very important player, which is electron, charge carrier, and they carry orbital angular momentum and spin angular momentum. The orbit and spin of the charge carrier, they are coupled by spin-orbital coupling, and for spin of the charge carrier is coupled with local magnetic moments by exchange interaction, such as RKKY type interaction in metallic system. For orbital, it doesn't directly interacts with local magnetic moments, but instead it rather couples to the lattice through crystal field potential, essentially just a Ligand potential. So in this fundamental perspective, spin-orbital torque can be understood as like this. So we perturb these orbital states by electric field, and something magical happens in a way that the orbital will take the angular momentum out of the lattice and will transfer its angular momentum to the spin through spin-orbital coupling. So in this talk, I'm going to focus on this mediation of the angular momentum through spin-orbital coupling and crystal potential through examples, like how the orbital takes angular momentum out of the lattice and then transfer to the spin. So in the first example, I'm going to introduce to you a phenomena called orbital Hall effect. So I'm going to answer the following questions. How can we generate orbital angular momentum in the solid through the interaction of the orbital and the lattice? And secondly, then how does it flow in solid once we generate it? Finally, then how does it transfer its angular momentum to the spin part of the wave function? So actually, the research on orbital Hall effect didn't start from nothing. It started from when I first started my PhD. And at that time, I wanted to understand the mechanism of the spin Hall effect. So I looked up some paper as a starting PhD student. And I found this paper, very famous paper by Hiroshima in 2004. And this very simple model called Rashba model, which also has this spin texture in K-space, predicts the intrinsic spin Hall effect. So I can definitely, you can also follow equation line by line, but intuitively, it's very clear that we can expect some sort of spin dynamics or spin transport, because that's my logic. So we have electric field, and electric field will induce the dynamics of the crystal momentum K. But with this coupling, K is coupled with spin. Therefore, it was quite natural to me that electric field will induce spin dynamics and transport. in this model. But one thing, important thing to notice is that this Rashba model applies to only inversion asymmetric system, for example, at the surface or at the interface in the solid or in polar material. But we know that a lot of bulk materials like gold, platinum, tungsten, tantalum, they are inversion symmetric. And also they have plenty of mirror planes. So there's no spin texture at all. So if you just calculate the electronic band structure of this material and also try to calculate the spin texture, which is essentially a spin expectation value for each eigenstate, then you find none of fingerprint of the spin in the K-space. So it was a very serious problem. I was really puzzled because, okay, if I just look at the electronic structure, there's nothing about spin. The information is very much hidden, but then how the spin coupled to crystal momentum and how the crystal momentum couples to electric field in turn. So this was the problem that I wanted to solve conceptually. And then after all the struggle, I came to the conclusion that there must be orbital. Well, as I first introduced in the first few slides. So to understand how the orbital play a role, let's introduce a concept of orbital texture, which basically describes the coupling between orbital wave function and the lattice. Orbital texture is not something totally new. I just name it as orbital texture, but it's essentially the change of the orbital character as a function of k. So this is quite routinely calculated by many people, especially from electronic structure community. For example, this is an example for p orbital materials. For p orbital materials, you can easily find this type of radial type texture and also this tangential type texture. And the characteristic of this texture is that it's the arrangement of the orbital character, not the orbital moment. Therefore, it doesn't necessarily require inversion symmetry breaking, like a Rashba effect or Dresselhaus effect. Sure, if you break the inversion symmetry, orbital moment can also be arranged in K-space, which is called orbital Rashba effect, but this is another topic. Here I'm going to focus more on central symmetric material, where we have only the orbital texture of the character. And the origin of this orbital texture is nothing but the direction of the chemical bonding in the solid and this direction-dependent hopping. So here is what I mean. Let's have a look at state here on the right side. If you look at this state, it is moving on the right side in K-space, in real space. So it means that for electron moving on the right side, they tend to have this px orbital. On the other hand, for state here, for states moving on in the y direction, then they tend to have y orbital. And this is due to the direction of the bonding in real space. So orbital texture is then nothing but a manifestation of orbital lattice interaction. So theoretically then, how do we describe this kind of orbital texture? Well, it's already there if you just calculate the band structure. But if you want to do analytic theory, you might consider this type of interaction, L.K square. And this interaction satisfies inversion symmetry and also time reversal symmetry. It appears first in this very famous paper by Bernabik, Hughes, and John. And as far as I know, this is the first paper that mentions a word called orbitronics. By the way, they didn't use the word orbital texture, but they solved this interaction in this paper. Okay, well, diagonalization of this interaction is very straightforward. You just, it's a simple quantum mechanics problem, exercise problem, and depending on the quantum number along the quantization axis k, we can easily find that quantum number 0 corresponds to the radial texture, like a p Z-like orbital is arranged in the direct direction of k, and lambda equals plus minus 1 corresponds to tangential type texture. So this is the ingredient that how the orbital wave function interacts with the lattice. So then let's see what happens if we apply an external electric field to the system. For demonstration purpose here, I will consider a very simple model, just two band. One is tangential type character, and the other is radial type texture. One thing important to notice is that here, if you calculate orbital angular momentum for each eigenstate, angular momentum is 0 for every state. It means that all orbital angular momentum is quenched. So there is no angular momentum in equilibrium, but let's see what happens in non-equilibrium driven by electric field. So if you apply electric field or current, this will shift the Fermi C like this. And let's have a look at this orbital. So we shifted the orbital here, but the orbital here, it doesn't want to stay in this shape anymore. Instead, it wants to be like in a tangential shape at this shifted K point. Because once we shift the K point, the way the wave function interacts with the lattice becomes different. Therefore, the orbital will somehow kind of experience the like a precession along the eigenaxis. So in equation, you can write down this wave function as a superposition of two eigenstate, tangential eigenstate, and radial eigenstates, and this coefficient will depend on change of the K caused by electric field. So as time goes on, they will separately evolve Hamiltonian evolution. Therefore, it will obtain the time dependence like this. So as time goes on, because the tangential energy and a radial band, they are separated by an energy gap, so the ratio will become complex number at the end. It means that like px plus ipy or px minus ipy states, like complex orbital, will be induced in non-equilibrium. So this implies that finite orbital moments will be induced in the steady states. So if you follow this analysis for every part of the K-space, we find the following. So in the upper part of K-space, we find the induced orbital moment with positive sign, and the opposite occurs in the negative sign. So this implies that here, so we have these states are moving to the plus y direction, and states here, they are moving to the minus y direction. It implies that, okay, we have the orbital dependent velocity that is nothing but the orbital Hall effect. So the orbital up and orbital down state, they are moving to the opposite direction. So this is orbital Hall effect. So, so far I did the simple model analysis in 2 dimensions, but if you do the same thing for 3-dimensional system, we find that induced orbital moment caused by electric field in the steady state will be proportional to electric field times crystal momentum K. So here we again find the orbital dependent velocity will be induced in non-equilibrium. So this is the K-space picture of the orbital Hall effect and what happens in real space. Okay, to understand what is orbital current in real space, it's very useful to consider a wave packet. So with some weight function for each K point, we can consider a wave packet forming out of this superposition between radial and tangential type block states. And the ratio is determined where we are at the K space and also depending on the electric field. But anyway, in non-equilibrium, in the steady state, this ratio could be complex number as we discussed. So in terms of wave packets, somehow the C, CR, and CT, they mathematically, they really acts like a spin, like internal degree of freedom for the wave packet. And we can understand this like this. The size of the wave packet is much larger than the atomic orbital size. It means that for the wave packet, the information of the orbital, that is this coefficient CR and CT, it acts like an internal degree of freedom. So this is an example of emergent degree of freedom. It means that orbital degree of freedom is not the fundamental degree of freedom for electron, for free electron. Spin is fundamental degree, but orbital is not. It's just one solution in in the atom. But in the solid, as a collection of atoms, this orbital information can act like an internal degree, like a spin, and this is called, again, emergence degree of freedom. So we can, there's an orbital current as the movement of this wave packet with this internal information, internal degree of freedom, C numbers. So this is how we understand the orbital current in real space. And if you still don't get it, don't worry. You could imagine an image like this. So in this video, I'm going to show you how the orbital current flow if you apply electric field. And well, at least to me, imagine orbital Hall effect as the following. So atoms will rotate around each atom. Electron will rotate around each atom like this, and it will hop from one side to the other like this. So intuitively, yeah, this is the orbital Hall current. Okay, so far we discussed then how we can then generate orbital current by taking angular momentum out of the lattice through orbital lattice interaction. And then let's see then what happens if we have spin-orbit coupling, and then how does this orbital angular momentum will be transferred to the spin part of the wave function. First of all, we saw that the previous mechanism, orbital texture mechanism, doesn't depend on the spin-orbit coupling. So orbital Hall effect occurs independent of the spin-orbit coupling. And then the role of the spin-orbit coupling is to arrange the spin moment to the orbital moment in the following way. And it depends on the correlation L and S. And it depends on material to material. And this behavior explains a Hund-like behavior of the spin Hall effect. What I mean is that if you look at the periodic table and just calculate or measure the spin Hall conductivity, and we find that this left part of the D transition metal, they have negative spin Hall angle, and on the right side, they show a positive spin Hall angles. And it can be understood in a way that this LS correlation is negative for the left part because the D shell is less than half filled, but on the right side, the D shell is more than half filled. So therefore, correlation is positive. Therefore, it explains the sign change of the spin Hall effect. This has been already noticed by this very important paper more than 10 years ago. And this paper explained that sign change of the spin Hall conductivity is due to orbital Hall conductivity, which doesn't change sign, even though we change the electron filling in the d orbitals. So then let's come to the very important question. How can we measure orbital Hall effect? Okay, you might have noticed that orbital Hall effect is very similar to spin Hall effect. So in terms of symmetry, the symmetry of the orbital Hall current is exactly the same as spin Hall effect. Therefore, I believe that a lot of experimental tools that we already have to measure spin Hall effect can actually measure orbital Hall effect. For example, in this experiment in 2017 from the research group in ETH Zurich, and they measured spin accumulation caused by spin Hall effect through a longitudinal Moog setup for platinum and tungsten. So they measured spin accumulation, but I was just curious, so I calculated actually spin accumulation and orbital accumulation caused by spin Hall and orbital Hall effects in platinum film. Here I considered platinum 111 stacking of 19 layers, and when I apply electric field into X direction, into the direction of this plane, then I found that orbital accumulation and spin accumulation occur together with the order of, in a similar order of magnitude. So I do believe that this orbital accumulation should be measured as well with the spin accumulation. So Moog can be a good candidate for measuring orbital Hall effect. Also, I think XMCD play a very important role because, for example, in the case of platinum, orbital accumulation and spin accumulation occur together. Therefore, XMCD, by using some rule, they can differentiate orbital and spin signals separately. Another important way to measure is actually to measure spin-orbital torque that I call orbital torque. This is the orbital contribution to the torque, which I'm going to discuss more in detail in the next part of the talk. And also, similarly, we can think of some non-local transport measurement as people have employed to measure spin Hall effect in whole bar geometry. Importantly, to measure orbital Hall effect, I think using light elements can be very good because it doesn't depend on spin-orbit interaction. Therefore, orbital Hall effect can be gigantic even for light elements. In this paper, we calculated orbital Hall effect in 3D transition metals mostly, and then found that the magnitude of the orbital Hall effects are very large. Compared to spin Hall effect in platinum, the spin Hall effect in platinum, the level is around here, about 2,000. But the magnitude of the orbital Hall effect is about at least 2 times, 3 times, or 4 times larger. So the signal should be much more pronounced than the spin accumulation, I believe. Talking about material, there has been also very interesting developments in 2-dimensional materials. In this paper, they looked at transition metal dichalcogenide, which is very popular among 2-dimensional material candidates. And they show that it also shows a very large orbital Hall effect. But the mechanism is slightly different than the central symmetric system. But because here the MOS2 already inversion symmetry is broken, therefore orbital moment is already formed for each valley. But different valleys, they have different signs of the orbital moment. But the Berry curvature is also valley dependent, as is well known for like valley Hall effect. Therefore, this Berry curvature drives the Hall effect of this already existing orbital moment in each valley, and it leads to the orbital Hall effect in MOS2 or MOT2, which is also locked together with the valley information. And around the same time, interestingly, these people also found the orbital Hall effect in the same system. And surprisingly, they found that in MOS2 and MOT2, molybdenum telluride 2, they found that orbital Hall conductivity is constant even in the gap. It means that this material is orbital Hall insulator. But for spin, which is shown as this red line, spin Hall conductivity is 0 in the gap because this material is topologically trivial in terms of C2 classification scheme. But for orbital, it is not. But this is not quantized. So in this paper, they explain the origin of orbital Hall effect in terms of orbital texture, which is rather orbital moment texture because inversion symmetry is broken. And this exists even without spin-orbit coupling. So the orbital Hall effect in MOS2 also doesn't depend on spin-orbit coupling. So the question actually I have is the following. For the case of spin Hall insulator, for example, in this paper, a very important paper in the development of quantum spin Hall effect in the next years, and also topological insulator. And this concept of spin Hall insulating phase played a significant role for finding topological phase that we have nowadays. Then my question is, what is the meaning of this finding for orbital Hall insulator? Is it really belonging to the current scheme of topological phase, like a 10-fold classification, or this is something totally new? I don't know the answer, but in this talk, I just wanted to throw the stone, as I'm not an expert, but maybe somebody will pick up this problem and maybe find something amazing. But I do believe that 2D materials, there are also lots of possibilities that you may explore. So from now on, I'm going to change the gear into how we can induce torque by utilizing orbital current. I would like to emphasize that this orbital torque is currently a missing piece in spin-orbit torque research field. So I'm looking for experimental signature. So if you find any experimental signature that looks like orbital torque, which I'm going to explain, I'll be happy to discuss. So the idea actually started from the ICM meeting 2 years back. And then I discussed with Dr. Kim and Professor Otani in the meeting, and they told me that, okay, they observed very large spin-orbital torque in a supposedly trivial system. And trivial means that it didn't have any heavy elements like tungsten or platinum or any kind of spin-orbit source, but they still observed very large torque. And then I got an idea that, okay, it might be orbital, but I wasn't sure. But okay, then I came up with this following mechanism. So here, okay, first of all, spin Hall effect can occur from non-magnet. So we can generate orbital current, and orbital current can be injected into the ferromagnet. But because orbital cannot directly talk to the local moment, it has to be coupled to the spin in the ferromagnet. Therefore, it requires spin-orbit coupling of the ferromagnet. Although the spin-orbit coupling in the ferromagnet is quite small compared to other heavy elements, but it exists in principle. Finally, the spin coupled with orbital exert torque on the local moments. So when I first came up with this idea, I wasn't like fully sure. It was like half and half. Because in one side, I was positive because the orbital Hall current, as I shown you before, can be really gigantic. Typically, this can be like 10 times larger than spin Hall effect. As an example, if I look at tantalum or tungsten, I calculate orbital Hall current and spin Hall current. They differ by 30 times. Orbital Hall current is 30 times larger than spin Hall current in tantalum and tungsten. So it can really play a significant role. But on the other hand, I was a bit worried because spin-orbit coupling in the ferromagnet is not very large. But at the end, after the simulation of some model system, also in real system, we find that actually these two effects, the negative effect in the ferromagnet due to spin-orbit coupling and also positive effect due to gigantic orbital effect kind of cancel each other. Therefore, at the end, it gives more or less similar size of the torque as a typical spin-orbit torque. And this is one result of our tight binding model calculation. And here I consider very simple model, 20 layers of non-magnetic layer and 10 layers of ferromagnet. And I intentionally switched off all the spin-orbit interaction in non-magnet and turned on spin-orbit coupling only in the ferromagnet. And this white line shows the response of the orbital accumulation before I attached the ferromagnet and non-magnet. So we see that the accumulation of the orbital in an asymmetric way, and this is due to orbital Hall effect in non-magnet. But as soon as we attach the sample, then we have an injection of the orbital shown by these blue dots. And also, because we have spin-orbit coupling, we have spin accumulation as well. So this is exactly as I expected in a schematically. Interestingly, we also find this constant value of spin accumulation in the non-magnet. And at first, it was very weird, but this can be understood as the following. So in non-magnet, at first, the electron is not spin polarized. Then it is injected to the ferromagnet. And some part of the electron will be reflected from the interface. But spin will be polarized because in the ferromagnet, spin-orbit coupling exists. But so this finite spin polarization should decay if we have any relaxation mechanism. But here in the non-magnet, by the setup of the model, because there's no spin-orbit coupling, so spin doesn't relax. Therefore, spin accumulation is just constant over all region of the non-magnetic sample. But in reality, with finite spin-orbit coupling, this signal should decay with some characteristic length. So this one corresponds to field-like torque. Remember that spin is what is responsible for the torque, not the orbital. So we have to look at the signal of the spin. And I also calculated the other component of spin accumulation and orbital accumulation. And we found that spin and orbital, they are locked together and they oscillatory and decay together. And this is somehow similar to the decaying and oscillatory behavior of the spin transfer torque. But this happens together with spin and orbital locked together in orbital torque mechanism. And this component is related to a damping line torque. So after the calculation with reasonably chosen parameter range, I concluded that the amount of spin accumulation is actually as large as spin-orbit torque that we actually find in platinum cobalt system, for example. So orbital torque can be sizable as conventional spin hole torque. That's the conclusion that I drew at that time. So then let's come to another fundamental aspect. How does the orbital injection occur at the interface? So how does px plus ipy state can be transferred to the next layer in the atom? And this happens through some orbital hopping. Like for example, px orbital can hop through sigma hopping as shown here, and py orbital can hop through pi hopping. But hopping from px to py is forbidden. Therefore, this superposition px plus ipy will be maintained even after the hopping. The same thing can also can be considered in d orbital system. For example, the xy orbital can hop by the pi hopping, and the yz state can hop by delta hopping. But hopping from xy to yz is impossible, because for this hopping, we have the mirror plane, so the hopping integral is a 0 due to the existence of mirror plane. So there is some lessons drawn from this consideration. The first lesson is that the injection efficiency should depend significantly on the interface crystallinity, because once we have the interface disorder, then this hopping will be randomized. And once we have disorder interface with some corrugation, this kind of selection rule for the orbital hopping will not hold anymore. So therefore, I think interface crystallinity should play a very important role for orbital injection. So this is quite different from spin injection. Secondly, we notice that the hopping amplitude for px and py are differ. Also, the pi hopping and the delta hopping, they differ. Therefore, the difference of the hopping amplitude implies that there must be the intrinsic decay length of the orbital, because the ratio, well, at first it started from 1 to 1, but the ratio could actually be different as time goes on with hoppings. Therefore, there must be some intrinsic decay length for orbital injection. According to my experience so far, I think this decay occurs in a couple of atomic layers in metallic regime. But it may be much larger, maybe, I don't know. We need to study more systematic way. Okay, I'll give you a small quiz. What about the then transfer of the p orbital angular momentum to the d orbital? Do you think it's going to be possible? So I'll give you like 10 seconds. So think about the answer. So from p to orbital, is it possible to transfer like p orbital moment to the d orbital moment, although they are different? Okay, the answer is yes. You could also consider this kind of hopping integral and which kind of hoppings are allowed for p and d pairs. This is essentially a Slater-Costa parameter, and you can always find the two pairs where this information of the orbital superposition is maintained in a way that orbital moment is transferred from p to d. So you don't have to worry which orbital, like p or d, we are talking about. So let's summarize what is the characteristic of the orbital torque compared with spin torque. So for spin hole torque, the origin is spin hole effect and is from the spin injection. And this is quite similar to spin transfer torque. Just the spin current is induced by spin hole effect. So what is responsible here is spin-orbit coupling in the non-magnet. And usually, also for the spin transfer torque, the choice of the ferromagnet is not so significant. Also, interfacial disorder should not matter significantly, especially when spin-orbit coupling is small, because there's no way the spin can relax unless we have spin-orbit coupling. But for orbital torque, things are quite different. First, it occurs from orbital Hall effect from non-magnet or other source of orbital current, and orbital should couple to spin, and spin will exert torque to the magnetization. And here, spin-orbit coupling in the ferromagnet is important rather than spin-orbit coupling in non-magnet. And this should also occur although spin-orbit coupling in non-magnet is quite negligible, like in light elements. And importantly, also for orbital injection, interface disorder is very significant for injection efficiency. And this doesn't have any analog for the spin injection. Oh, sorry. So, but unfortunately, it's really hard to tell which one comes from spin torque and which torque comes from orbital torque. That's very bad news, especially to experimentalists, I think. Also for theorists, sure. Because the symmetry of the torque are the same for orbital and spin torques. It implies that they actually, in real sample, they can add up or cancel each other depending on the situation. And the condition for the cancellation or adding up depends on spin-orbit correlation of the non-magnet together with the spin-orbit correlation in the ferromagnet. So spin-orbit correlation is usually positive for a 3D transition metal compound, and it's negative for gadolinium. But for non-magnet, we know that platinum is one example for positive correlation, and tantalum and tungsten are negative correlation examples. So let's have a look at more concrete example here. So here, the spin-orbit correlation and non-magnet, they are opposite to each other. Therefore, in the non-magnet, spin Hall and orbital Hall effects, they are occurring in different signs. So they inject with different signs. But because the spin-orbit correlation, the ferromagnet is positive, so spin and orbital direction should be parallel. Therefore, at the end, the torque caused by spin, shown here, and the torque caused by orbital, they compete each other and they cancel each other. One example is that I recently found is iron or nickel on top of tungsten 110 substrate. In this case, spin Hall conductivity is negative, but orbital Hall conductivity is positive. But the strength of spin-orbit correlation is different for iron nickel. Therefore, it leads to different behavior. Especially for nickel case, this orbital contribution becomes really large that actually it's strong enough that orbital torque can flip the sign of the effective spin Hall angle. But for the case of iron case, we found that the spin Hall angle is just, as is well known. For nickel, it's quite anomalous. So I think this can be readily measured by experiment. Just measure the torque and see the sign, whether the sign is positive or negative. So and then, okay, because spin and orbital torque, they are really difficult to disintegrate. So we have to come back to somehow to the beginning that I showed you. So in this paper, that actually a lot of authors contributed to this paper, we analyzed how angular momentum is transferred from different channels, like how orbital and lattice interact, and how orbital and spin interacts, and how spin and local moment interact in every part of the magnetic bilayer structure. And this is done by continuity equation for spin and orbital. For spin, for example, we have spin current flux and also exchange torque. This describes the interaction, angular momentum exchange between spin and local moment, and also by so-called spin orbital torque that we named. This one describes the angular momentum transfer between spin and orbital part of the wave function. We can do same thing for the orbital. First of all, we have orbital current flux. Also, we find the crystal field torque. This describes the the moment transfer between lattice and orbital through crystal field potential. Again, we also have a mutual transfer of angular momentum between spin or orbital, also for orbital. So this is kind of back to the beginning because this approach has already appeared in this paper by Henny and Strauss in 2010, which is very at the early age of spin-orbit torque. But I think it's now time to reconsider this approach because the situation is getting more and more complicated. Because we have not only spin Hall torque and orbital Hall torque, we also have different kind of torques. So in this paper, we also propose how we can classify torques in the magnetic bilayer depending on some criteria. One is which spin-orbit coupling is responsible, whether non-magnetic spin-orbit coupling is responsible, and whether ferromagnetic spin-orbit coupling is responsible. And also, we divided this one by where the current is flowing. For example, when current is flowing in non-magnet and we see the response in the torque, we call it no-local response. In the other case, current flows in the ferromagnet and we see the response also in the same spot, we call it local. So for non-local and non-magnetic spin-orbit coupling origin is the spin torque. So current flows here and we see the torque here due to spin-orbit coupling in a non-magnet. And local torque caused by non-magnetic spin-orbit coupling is one type is interfacial torque. For example, current flowing from in the ferromagnet can scatter from the non-magnetic substrate with spin-orbit coupling, and it comes back to the ferromagnet. And third, with spin-orbit coupling, spin-orbit coupling in the ferromagnet and no local current in the non-magnet, this is nothing but orbital torque. And finally, when the current flows in the ferromagnet, and then we see the response in the spin-orbit coupling in the ferromagnet, and also current flows in the same spot, there could be spin Hall effect. But due to inversion asymmetry in this system, spin current flowing in the downward direction is actually lost to the non-magnet. Therefore, the accumulation of spin upper part can exert finite torque. So this is actually called anomalous spin torque. And this has been recently measured by Sin Fan's group, and is published in this paper. By the way, about the interfacial torque, the definition of the interfacial torque here is very restrictive. It's a bit different from the general definition. So for detail, please have a look at also this nice review, which appeared, I think, in this week or previous week on arXiv. Finally, I'd like to mention a few experimental signatures that I think it could be orbital torque, but not fully sure. But here it goes. So copper is usually known to be a very inert material in terms of spin torque generation because spin-orbit coupling is pretty small. But for some reason, they oxidized the copper layer naturally from the air. Maybe it could be from the mistake, or I don't know, they intended. But anyhow, they measured the very large torque comparable to any conventional spin-orbit torque system like platinum cobalt. So it's very surprising results, but we couldn't really understand the mechanism. And then later on, they continued their research, and they found that it somehow is related to the concentration of the oxidant very sensitively, and it's related to orbital hybridization. So it's somehow related to orbital physics, and then I got interested in this system. And this year, they published a preprint on arXiv, and they claim that it actually could be from orbital torque. And in this manuscript, actually, they compared with other possible explanations known so far and concluded that the orbital torque is the most plausible explanation. And the key evidence here is that they found the sign of the torque is opposite for permalloy case and iron case. So this is exactly the orbital torque predicted because it depends on spin-orbit coupling of the ferromagnet. So they saw the sign change of the torque depending on the ferromagnet. So interestingly, from this idea, Shirley Ding from Matthias Chloe's group in Mainz, he performed the experiment with surface oxidized copper. But his idea was not only use this copper oxide, but insert a platinum layer, because the idea that he had was that once we have this orbital generation caused by copper oxide as conjectured by Kazuya Ando's results, this orbital should be very efficiently coupled to spin due to platinum, because spin-orbital coupling is very strong, as is well known, and is quite reliably known, I think. And then this coupled spinor orbital will exert a torque. And surprisingly, it was actually the case we found. For series A, is the case without copper oxide layer, and simply follows the hyperbolic sign behavior as a function of platinum thickness. But as soon as he added copper oxide layer on top and oxidized from the air, and we saw significantly large enhancement of the torque, really like 30 times larger than just a bare platinum case. And by taking the difference of the two, we could extract the contribution from the orbital injection, and we found that, okay, that its torque can be very large, and it's very likely that orbital plays a role as well, and it's quite consistent also with the results from Kazuya Ando's group. So I think this can also be, this is also a very important discovery toward the characterization of the orbital current. Finally, there has been an experiment by Junyoung Kim from Professor Otani's group, and in this case, they didn't oxidize copper from the air, but they used aluminum oxide capping instead. But because this capping is pretty stable, so oxidant concentration is not very large as naturally oxidized case, but still the inversion symmetry is significantly broken at the interface by the existence of the capping layer. But the surprising result that they have found is that the torque efficiency changes really dramatically for different ferromagnetic compound. Also, it changes a lot even for cobalt iron, it changes really a lot for different annealing temperatures. So we were really curious why it happens. And we took an image from TEM measurement, and we found that for the case of nickel, which doesn't show actually any torque, actually, and the interface is quite corrugated and it's quite dirty. Actually, we also found that for copper and nickel case, it is quite well known that they tend to mix each other, and magnetic dead layer is formed at the interface. So somehow magnetic dead layer, which is quite corrugated, seems to block some orbital or spin injection. But on the other hand, for cobalt iron case, when it's annealed at 300 Kelvin, 300 Celsius, sorry, and we found a very almost atomically aligned texture at the interface. So from this observation, we see that the interface disorder, interface crystallinity between copper layer and ferromagnetic layer seem to play a very important role. And this seemed to agree with, as predicted by orbital torque mechanism. So we believe that not only naturally oxidized system, but also this capping layer, copper with capping layer, also exhibits orbital torque behavior. But I'd like to emphasize that still, we don't have very conclusive evidence. Frankly speaking, I don't really know actually how we can conclusively say that this is orbital torque, but from many circumstances, we think this is due to orbital torque. And to really see what happens in copper, because copper doesn't do anything in terms of spin, we actually calculated orbital texture in copper. What happens if we break the symmetry? So without inverted symmetry breaking, we saw that the orbital texture is quite almost zero. This is arbitrary unit, which is actually very small. I wanted to indicate that there something exists, like positive and negative appears, but overall texture cancel to zero. But once we apply some inverted symmetry breaking field in our tight binding model, and we found that the orbital texture can be significantly enhanced. And we were very surprised with this result at first, because for copper, the Fermi surface state is usually mostly s orbital character, which doesn't carry any orbital moment. But we found that with the breaking inverter symmetry, the d orbital states come close to the Fermi energy, and these d orbital states near the Fermi energy can have significantly pronounced orbital texture shown like this. So I think this might be the origin of the generation of the orbital, but more systematic study is required. So let me summarize that I explain you that by orbital texture, it captures coupling between orbital and its interaction with the lattice, and we can induce orbital Hall effect. And orbital Hall effect can transfer spin moment to its orbital moment to the spin through spin-orbital interaction. And by utilizing this orbital current, we can have another mechanism of the torque called orbital torque, and this is still missing. So we are looking for experimental signature of the orbital torque and orbital Hall effect. So if you have any idea or any suspicious data, I'll be happy to share my opinion and happy to collaborate. Also, among other material systems discussed, experimented so far, I think surface oxidized copper or oxide-capped copper layer could be efficient candidates for efficient orbital generator. So most of all, orbital degree freedom is not only just a different topic than spintronics, but it's rather very important degree freedom to understand spin orbit physics in a more fundamental level. So if there is only one picture that I want you to remember after this talk, it's just this one on the left bottom. So if you just remember this picture, that how the orbital mediates its interaction with the lattice and spin, then I think you got most of the message. So thanks a lot for your attention, and please join the orbit. Finally, also, I'd like to acknowledge my collaborators. A lot of people from ULISH, also from Mainz, and also from my former group in PostTech, and also a lot of collaborators from Japan, Korea, and United States. And I would also like to acknowledge the funding from Spin+X and Talk Team. So now the talk is open for question.
Thank you very much, Dongwook, for this
Thank you.
talk. So we're now going to take questions. So in Zoom, just use the raise hand feature. If you're watching on Twitch, just type your question in the chat box and I'll read it for you. So first question, Ran Chang, please go ahead.
Hello.
Hello.
Hi. Thanks very much for your talk. So I have two questions. First one, okay. So in your picture, it seems that the ferromagnet has to be metallic, yes. So that you know the electron flows into the ferromagnet and then changes the spin, therefore exerting a torque. So I was wondering if the orbital torque still exists if I consider a insulating ferromagnet,
like E or T, for example, like, right?
Yeah, for example. So basically my question is, if the electron, you know, get 100% reflected on the interface, will the spin-orbit coupling on the ferromagnetic side also results in a torque? So that's the first question. The second question is, we know that in studying the spin Hall effect and electronic spin currents, then we can define a effective spin chemical potential.
Yes.
So I was wondering if we can define an orbital chemical potential to characterize the orbital current. Thanks very much.
Yeah, thank you very much for very nice questions. That it's very nice that you raised this question. First question is that whether the orbital torque can exist also for ferromagnetic insulator like EEG. And for the moment, frankly speaking, I do not know. But in my gut feeling, I think it might be small because the exchange coupling mechanism, the torque mechanism in magnetic insulator is slightly different from metallic case because it is mediated by proximity exchange interaction. But for orbital, I don't think this can be mediated by this proximity exchange interaction, but I'm not fully sure. It might be possible, but we need to study more in detail. I'm sorry about this. And for the second question was that whether we can define some concept like orbital dependent chemical potential, like for the case of spin. And it is actually very important to do to develop this field. For example, like we may be able to develop like orbital dependent diffusion equation, like for the case of spin, and also like magneto-electric circuit theory, for example, for the orbital as well. So it's very important to define orbital dependent chemical potential, but this is currently very difficult to do because the idea of spin dependent chemical potential is that spin is almost the eigenstate of the flux of the system, so that we can define like, we can imagine like two current model. So that's how we can define spin dependent chemical potential. So it's a roughly conserved quantity. But for orbital, it's the eigenstate is not, doesn't carry orbital moment. It's rather more excited states. So that is the most difficult part, that why I couldn't do actually this kind of work, because I really wanted to do. But if you have any idea, I don't think, why not? But so my answer is it's very important, but it seems to be very difficult for the moment. So I'm sorry that all the questions, all my answers are quite negative.
Thanks very much.
You're welcome.
Thank you. Matthias, please go ahead.
Yeah, so Dongwook, actually, thanks for this very nice talk. A question and a comment. The question is, now if we do XMCD imaging to get the orbital current, we cannot image a current, we can image an accumulation.
Accumulation, yes.
Yeah, so what would be a good geometry to get an orbital current or orbital spin accumulation, so to speak? Or orbital, whatever you call it, angular momentum accumulation.
Yeah, this can be done by a longitudinal Mach setup, which was already done by Pietro Gambadella's group 3 years back. And what they have done is that, okay, in this sample, they inject the current into the plane to X direction, and then spin will be injected on top and bottom surfaces. Here, top spin is accumulated, and also in the bottom, spin is accumulated. But for the case of Mach, we have a reflection, and most of the interaction occurs at the top surface. Therefore, in the Mach, they could measure. But for XMCD, it's a little bit tricky because it's very high energy and it penetrates through the sample. So I think transverse geometry is better in a way that if we can spatially resolve the accumulation in the boundary. But I talked to couple of people in the past, to XMCD guys, and they told me that in some case, with very fine tuning of the instrument, they can focus the beam, but it requires a lot of effort, as far as I know. But I think.
So you suggest to go for the same geometry, but replace platinum or tungsten, which has a normal spin Hall effect, by a different material with the Hall, with the orbital Hall effect.
Yes, if you use Mach. Okay. Also, if you remember the experiments by Kato from Ashlam's group, one may also perform such kind of experiments for orbital as well.
Okay.
But this requires a very narrow focus of the beam. I think that is quite challenging.
Okay, and then maybe just the comment, just for the community, one should say that all the praise should go to Dongwook for the explanation of our experiments. I mean, we just did the experiments and didn't understand shit, and, and he explained it to us. And maybe just a comment also to Ren Cheng. So we actually used thulium ion garnet. So we used an insulator, but we had additionally the platinum layer to convert the orbital Hall current into a spin current. So that in the end you had the spin current acting on the insulating ferromagnet or ferrimagnet. So it was kind of slightly different from what Ren Cheng was asking. But if you do that, then of course you can work also on insulating ferrimagnets. Okay.
Exactly. I think so. Yeah, this is very nice setup because I thought that orbital will not be interacting with the insulating magnet, but by inserting additional metallic layer with strong spin-orbit coupling, we can somehow interact the orbital and spin through the spin-orbit coupling in the platinum layer. Yeah, thanks for the comment.
All right, thank you. Shin, please go ahead.
Yeah, actually, thank you very much for the talk. Actually, before I ask you a question, I want to ask Matthias a question about that that paper. Just follow up as a follow-up question. Did you try to replace platinum with copper?
Yeah, we have actually lots of data. So actually, Shilei, who is the PhD student who did all the work, is also here. He can probably answer best what all the stuff we tried. But maybe we can leave this to later when we have more time.
Yeah,
but
we can discuss that later.
Shilei should also get the other half of the praise.
Yeah, it was an excellent experiment.
Yes, actually, yeah. My question is, I have a couple of them. Save some of them to later. But I think as Jan already asked, for experimentalists, typical force is like we can have different methods to measure the spin. But to distinguish from different mechanisms, what we do is thickness dependence, slightly modify the interface, insert a spacer layer, and that's pretty much it. So what do you expect the length scale? Just like a spin, you have a spin diffusion length. What about the orbital current? How does the what's the typical decaying length? Is there any decaying length?
Okay.
I suppose it's related to crystal field, but
yeah, exactly. Okay, I'll answer in two different ways. For orbital relaxation length, for the spin-orbit coupled system like platinum, in this case, orbital and spin are pretty much locked together. Therefore, in this case, orbital diffusion decay length is pretty much the same as spin decay length because of strong spin-orbit interaction. But if we go to light elements with small spin-orbit interaction, and this is basically governed by this crystal field in the system, and I cannot say in a simple word, but just from my experiences from many different simulations, it seems to decay in a like 3 to 5 atomic layers. So it's just a 1 or 2 nanometer scale. So it's pretty short. It's because the energy scale that orbital interacts with the lattice is pretty large. Therefore, decay is very fast. There's an intrinsic decay, not with any defect in the system.
I see. Thank you. And also, I just want to say that whoever came out with the term spin-orbital torque is actually very good because you also have the orbit.
Actually, I was curious. But I was really curious because a lot of people talk about spin-orbit torque in the past years, but nobody really looked at orbital, really. But so I was really happy to also emphasize orbital aspect of the torque.
Yeah. Thanks.
Speaking about the decay length, it seems like, the mechanism you described was intrinsic, right? Because of the...
Yeah, more like intrinsic, yeah. Okay. Even without any disorder, it occurs already.
But if you think about, any sort of impurity scattering, it seems like as long as you relax momentum, you also lose the angular momentum, the orbital momentum. So I would think that the orbital diffusion length would be pretty much mean free path. So if you're getting just a few years, that's more or less what you would get in any sort of heterostructure due to impurity scattering. Would you agree?
Yeah, I agree. Yeah, especially for extrinsic mechanism for decay, it should be the length scale of the momentum relaxation, as you said.
Right.
Yeah. So I think there might be some competition between different relaxation, intrinsic or extrinsic. So maybe this could be a way.
When you say intrinsic relaxation, do you mean due to spin-orbit coupling?
No. Intrinsic means by crystal field, because already in the crystal, it breaks the rotation symmetry. So already orbital is not a good quantum number.
Yeah, but isn't that the generation mechanism actually? That you need that hybridization?
Yeah, it does. But I can do some kind of calculation like. In some layer, I can generate orbital, and the other layer, I can observe how it decays. You know what I mean? So I can kind of make a model that generation occurs only some part of the system, and then see how does it decay in the other part of the system.
So you mean you would turn off hybridization?
Yeah, exactly. Such that the orbital generation doesn't happen.
Yeah, but it's kind of equivalent to introducing impurities, isn't it? If you're changing the band structure locally, that's the same as if you relax. I mean, you also pattern.
Yeah, that is you are right. Yeah, exactly. That is right. Also, okay, sorry, I couldn't mention this, but sorry, there's a lot of slide. Okay, in this paper, actually, I also calculated thickness dependence as a function of non-magnetic layer. It's in supplementary material, I think, or in the main text. So, and the dependence also follows hyperbolic sign dependence, like a spin Hall effect. So that was also some surprising part that I found.
Okay. Okay. Alexei Kovalov, did you have a question?
Okay, so I just wonder, so how efficiently can this orbital current penetrate through interfaces?
How we can, visualize or understand?
How efficient is transfer of this orbital current through interfaces?
How resistant? I'm sorry.
How efficient?
Efficient. That's a good question. We can already see some part of the answer here in this plot. So here, without any connection between ferromagnet and non-magnet, the accumulation is pretty large here. But actually, once we connect the system, the injected one is pretty small. So I would say, I cannot estimate the exact ratio, but it should be very small. But even though it's small, the effect on the torque is sizable.
So what is the mechanism? Because if you're talking about intrinsic kind of effect, then it's not even clear how it can go through interface so efficiently.
Okay. The physical mechanism that I think is really like this kind of hopping at the interface. So for hopping, we have each pair of hopping happening for each orbital, and there's some kind of selection rule. And this selection rule gives the transfer of the these superposition states from one to the other. But the ratio becomes,
does it imply some kind of similarity between materials that you have on the left and on the right?
Yeah. It depends on similarity of the material. Yes, that's a very good point. I think the lattice structure should be as similar as possible. At least for now, that's the system that I investigated. But I think when the lattice structure becomes totally misaligned, and this kind of selection rule shouldn't occur, and therefore the orbital injection will be very much diminished.
All right, thank you.
You're welcome.
Okay, thank you very much. So it looks like we're out of questions. So let's thank Dongwook by using the...
Thank you. I really enjoyed.
Thank you very much. It was
nice
a
clap.
great talk.